So now let's talk about the shortest path problem and whether DFS algorithm works for weighted graph as well. Okay, so we are going to consider the so-called single source shortest path problem, or abbreviated as the SSSP, which is just given a weighted graph and the source node S, compute the shortest path distance from S to all other nodes in B. Okay, so again, recall that I use delta SU S to V to denote the distance, the shortest path distance from S to U. Okay, so in other words, you want to compute delta SU for all nodes U in your node set. Okay, and now this is this called single source shortest path because you're starting with the source node S, same as in the BFS. But if you want to compute the all pairs shortest path, if you want to compute the shortest path distance between all pairs of nodes, then you can simply run this single source shortest path V times, starting where you take every node as the source node. Okay. All right. And as we said earlier, that for the unweighted graph, we can view that as all the edges has weight 1. Okay. When all the edges weight 1, then the length of a path become equal to the number of edges in this path. Okay, and this is how we define distance earlier when we talk about BFS, when we define the length of the path. Okay, so as such, we know that the BFS can compute the shortest path distance for this kind of for graph with edge weight 1 already. Okay, so the question is that can BFS be generalized to compute the shortest path distance for arbitrary weighted graph? Okay. Well, unfortunately, you probably already expect this is not true. BFS idea doesn't work for for general weighted graph. Okay, so let's just look at this example. In this example, I started with the source node S. Okay, in BFS, I immediately reach A, B, and C. Okay, and then from A, we first explore its neighbor, and then we see D. So we figured out that, okay, in this case, the distance to A is 2, and distance to D is 3. This looks good, okay? However, in BFS, note that when we explore S, we immediately found B. So if you take the weight of this edge as its distance, 10, and the same here for 8, then turn out that this distance is wrong, because even though that I immediately discovered B, this is not the short. This is basically the quickest way, the smallest number of edges needed to find a B. But this is not the shortest path. The shortest path actually to B is going from S to A, and then from A to D, and then from D to 1. So the true shortest path distance from S to B should be 4. Okay, instead of 10. Okay, so BFS fails in this case because BFS immediately found B through one edge, and then which give us distance 10. Okay, now intuitively, what went wrong? Well, intuitively, BFS is a greedy algorithm. Okay, it keeps exploring nodes and increasing distance to the source. But at that time, the distance to the source is the number of number of edges needed to reach this node. Okay, so at the time that we explore a node, we found the correct shortest path distance to the source in terms of the number of edges. Okay, but if the edges has different non-equal weights, this shortest number of edges does not imply to the shortest distance. Okay, so finding the first, now we didn't find when we first time explore node, we no longer get the correct weighted distance to the source. Okay, all right. But later, in particular next time, we're going to see how can we still use this greedy idea to develop a shortest path algorithm for weighted graphs in next class. Okay, all right. But here, there's another approach that we can still leverage the BFS. Okay, so to solve SSP, let's assume now all edges has positive integers as weights. So 1, 2, 10, 100, and so on. Okay, so here's an idea to compute to solve the shortest path problem, single source in this case. Okay, so suppose we're given the source node S. Okay, we want to compute the shortest path distance from S to all other nodes. Okay, so we say that, okay, if all my edges have equal weights or have weight 1, then I can use BFS to help me to solve the shortest path problem. Okay, so how about that? If I have an edge with weight K, so if I have an edge, let's say that U and the V with the weight 5, what I can do is that I can replace this. I can modify my graph so that between U to V, I have 1, 2, 3, 4, 5. Each of them has weight 1. Okay, so for example, if your graph is the following, just as a simple example, S, U, V, let's say it's a very simple graph. Let's say this is 5, 1, 7. Okay, if this is my graph, okay, then I basically replace each one. Now from S to U, I replace this with 5 edges. Now here it's only weight 1, so it's still 1 edge. But from S to V, I replace with 7 edges. Okay, so now I get this new modified graph. Okay, I have more nodes now because these are all nodes. But and for this graph, I run BFS, starting from the source node. And now the BFS would figure out the distance to U will be 5, and the distance to V will be 5 plus 1, 6. Okay, in this new graph. So I first convert my weighted graph where edges could have unequal weights. I first make them into edges with equal edge weights, where every edge has weight 1. Okay, then I run BFS on this modified new graph. Okay, so this is an algorithm, and indeed it works if your input, the edge weights are all positive integers. Okay, so this is a valid algorithm. But what's wrong with this algorithm? Well, number 1, for this to work, I need the edges to have positive integer as the weights, right? Because I have to make them to be equal weights. Okay. Number 2, even for integer weighted graph, it can be very inefficient. So like in this case, I have 95 as the edge weight. Now I have to replace this single edge with 95 number of edges. Okay, so, and here it's 409. Then I have to replace this one with 409 edges. You are significantly increasing the size of the graph, which is really not necessary. Okay, so we can try to use BFS, but then this way, but it's not effective, not very efficient approach. Okay, all right, we want something better. Okay, and that's what we're going to talk about next.